Kia ora class, today we're looking at biomechanics and I'm going to help you understand some of the biomechanical principles that you need to know for this unit. So you might be asking yourself, what is biomechanics? Okay, we've looked at anatomy, which is muscles and their actions. Okay, we've looked at physiology, which is how the body responds to exercise. And now we're looking at biomechanics, okay, which is how the body moves. Okay, so we've got the actions, but what dictates the manner that those muscles work. So the first principle that we're going to look at is the center of gravity. Now the center of gravity is the single point at which all parts of an object are equally balanced. So in this first picture you can see that the center of gravity is this black dot, which is normally around a person's belly button. Now a person's center of gravity changes depending on their position of their body. So in this next picture, his body has changed from this first one. So that means his center of gravity has also changed as a result. So you can see the black dot has now gone a bit higher and it's above his belly button. Now a person's center of gravity can also lie outside their body. So he's bending over and you can see the center of gravity just lies outside his body. A good example of this is the Frisbee flop. Okay, when you're doing the Frisbee flop and high jump, your center of gravity lies outside of your body. Next biomechanical principle we're going to look at is base of support. Now base of support is the area underneath and between both feet. The wider someone's base of support, the more balanced the body. So in our example here we have Michael Jones, number 1. He's got his feet close together, and on our right we have Nicholas Jones, who's got his feet wide apart. So which of the two Jones boys has the better base of support and therefore more balanced? Correct, it is Nicholas Jones, our man on our right. Well done. Stability. Stability is the ability of the body to remain balanced. So in this picture on our left, he is stable, he is balanced in the water. Okay, and our picture on the right, he is unstable, he is not balanced in the water on his kayak. The next one we're going to look at is vertical line of gravity. So we've talked about the center of gravity. Okay, so the center of gravity for this person is also lying outside their body for this diver. The line of gravity is an imaginary line, okay, that passes directly through the center of gravity and down towards the ground. So stability and balance. So balance is the ability to stay upright or in control of your own body movements. So in this picture on the right, you can see our Kung Fu man Liam here has got his hands down. Okay, so first of all, what is that? That's right, that's his base of support. Okay, so if he widened his base of support, or if he lowered his center of gravity towards the ground, okay, then he's going to be more stable and more balanced. So if we look at these examples, these 4 examples we've got here, okay, these show what different sports need high stability and what sports don't require high stability. So we've got our football players and we've got our wrestlers down here. Okay, so our wrestlers, you can see, are quite low to the ground. Okay, they've got a wide base of support and therefore they're going to be more stable and harder to push over. Whereas on here for our sprinter starts and our swimming starters, their feet are quite close together. They don't need a wide base of support because they're not going to be tackled from anyone. They just need to go as fast as they can. Rightio, moving on to Newton's laws of motion. Now, his first law is what? That's right, inertia. His second law is acceleration. And his third law is reaction. So Newton's first law, okay, inertia. A body will maintain a state of rest or constant velocity unless acted on by an external force. Okay? In other words, this means a body will remain at rest or in motion unless acted upon by a force. In order to get a body moving, a force must overcome the body's tendency to remain at rest or inertia. The amount of inertia a body has depends on its mass. So if we look at this example here, Okay. In the back there, this big sumo wrestler, that's me. And then down here, we've got Jake Young. Okay. So out of these two people, who has the most inertia? No, it's not Jake Young. It's me, the big sumo wrestler. Okay. Now, if I have greater mass, therefore I have greater inertia. Okay. That means it is harder to move me because I have a lot more inertia than it is to move Jake, who has a lot less inertia. Okay. Newton's second law. The acceleration of an object is directly proportional to the force causing it. It is the same in the same direction as the force and is inversely proportional to the mass of the object. So when a force is applied to an object, it will move in the direction the force was applied. And depending on the size of the force and the size of the object will accelerate accordingly. A smaller object will move faster than a larger object, and a greater force will move an object faster than a smaller force. Okay, so if I am going to throw a tennis ball to Tane, okay, if I do not apply a big force to that, the ball is not going to travel as fast. Okay, and it's going to travel in the direction that the force is applied on that ball. In this example here, we can see that we have a small mass and a large mass. Okay. Now, as we explained from before, a small mass can have large acceleration. A large mass has smaller acceleration. Okay, and there is the formula: force equals mass times acceleration. Newton's third law. For every action, there is an equal and opposite reaction. Okay. So, if an athlete exerts a force on the ground to push off, say in basketball, volleyball, netball, the ground will exert an equal and opposite force on the athlete, pushing them up into the air. The first force of the athlete pushing into the ground is called an action force. Okay, so that's the action. It's them pushing into the ground. The second force, which is the reaction force, is when the body goes into the air. Okay, when the second body applies an opposing force back. Okay, now implications here: artificial turf, sand, and grass. So how is our equal and opposite reaction going to be applied on different types of turf? Okay, so if we had someone jump as high as they can on artificial turf, on sand, and on grass, on what will they jump the highest? Okay, time for you to answer that. So, firstly, artificial turf, they would jump the highest because they would have the most reaction force, because the artificial turf is the hardest, followed by the grass and then the sand, because the sand is not very hard, so therefore the reaction force is not going to be as large. I'm sure you've all seen one of these, okay, and they go ding, 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 ding. Okay, so that's a good example of Newton's forces there. Imagine pushing on a solid wall with a fairly large force. The wall doesn't move. Why? So remember back to Newton's laws. Why would the wall not move? Okay, the wall will be exerting an equal and opposite force back on you. That is why. Lastly, if we just look at these examples, we can see our sprinter. Okay, he's got the action, reaction, a guy doing a bench press, action, reaction, and a guy bouncing the basketball, action, reaction. Okay, hopefully these biomechanical principles make sense to you. If not, ask me questions, or you can just watch this awesome video again. Sweet!